All right, another limit. Hopefully we get to use L'Hopital's rule in this one, and it actually works. We'll find out. So if I do, if I plug in infinity to each of these, what is happening? Now, in order for me to help me think about this, I think of the natural log function. So I graph it really quick. Here's my natural log function. That's what it looks like, roughly. And then as we think about it, if we're going to infinity on the x-axis, it looks like that arrow is going up and to the right. And so that means that is also approaching infinity. And it looks like with both of the top and the bottom, inside the natural logs, both of those numbers inside the natural logs are getting huge. And so that since they're both approaching infinity, the +1 and the +2 don't really matter. We know that we get infinity over infinity. And so that means L'Hopital's rule time. All right, let's hope that this works better off this time. So the derivative of natural log is 1 over x. Or you can say 1 over anything that's inside of x, or inside of the log. And then we have to multiply that by the derivative of the inside. And so that's our numerator. For our denominator, we get 1 over 2 plus x. And then we got to multiply that by 1, because the derivative of the inside of 2 plus x is just 1. All right, so what we're going to do is we're going to take the limit of this as it approaches infinity. I'm not going to simplify it just because I want to see what happens first. So the limit of this is x approaches infinity. All right, let's look at the denominator really quick because I see a problem right away. If I have a number right here that is going towards infinity, this fraction is going to approach 0. And if this fraction is approaching 0, 0 times 1 is 0. So right now we have a problem because we have a 0 in the denominator, and that's undefined. Up on top, we're going to have the same scenario happening. We have a fraction right here that is going to approach 0 if the denominator gets infinitely big. And 0 times anything is just going to be 0. So on the top, we have 0. Okay. So let's see if we can use L'Hopital's rule again and fix this problem. So I'm going to put this 3x to the second power on top. And then I don't need that times 1 anymore. I could probably multiply by the reciprocal to try to simplify this a little more, but I'm not going to do that. I'm just going to take the derivative of the top and the bottom using the quotient rule. I changed my mind. I'm going to multiply the top by the reciprocal of the bottom. So that means this simplifies to 3x squared, 2 plus x, and then we have 1 plus x to the third. No, dang, check that out. It looks like I think I could take the limit of that as x approaches infinity. Let's go ahead and simplify it just a little bit more. On the top, we get 6x to the second plus 3x to the third, and on the bottom, we have 1 plus x to the third. Now, if we were to take the limit of this as x approaches infinity, we would still get infinity over infinity. But there's an easy trick that we can do to every one of these terms. There's 4 terms, and for every one of these terms, we're going to divide each of these terms by the highest degreed variable. So that means I'm going to divide this by x to the third. I'm going to divide this by x to the third. And I'm going to divide, actually not the highest, the second highest. Never mind. Sorry, I don't know what I'm talking about. And I divide that by x to the third and divide that by x to the third. Let's see what we get. Let's simplify all that and see what we get. All right, man, I'm running out of space here. All right, so I got the limit as x approaches infinity, and this is my new manipulated inside. We have 6 divided by x plus 3. And then we have 1 divided by x to the third plus 1. And now if we plug in infinity, it would go into this fraction, and that fraction would go to 0. It would go into this fraction, and this fraction would go to 0. Whenever the denominator is approaching infinity, it goes to 0. It looks like our answer is 3. So let's go ahead and circle that. That one's finally done. Another limit. Okay, so when we look at this one, and you're thinking about plugging in 0, you go straight to plugging stuff in. You plug 0 into sine, and that's not a big deal. That's sine of 0 is 0, so you have 1 plus 0. So on the top you get 1. But then you plug 0 in the denominator, and you get divided by 0, and you can't have that. Unfortunately, if you have 1 divided by 0, that is not an indeterminate form, but we don't get a result. And so we want to see if we can manipulate this to see if we can get a result. Now, one trick we can do is we can split this fraction up, because I see something right here. I see a sine x over x, and there is something way back in chapter 2 that we learned, and that is whenever you're approaching 0 with sine x over x, that equals 1. So let's go forth and see what happens. So we can split this up. So we have 1 over x, and then the limit as x approaches 0 from the positive side was sine x over x. Okay, you might be confused as to how that just happened. I hope you're not too confused. Now, if you look at this fraction right here and this fraction right here, they both have common denominators. If I were to add these two fractions, I would get right back to this. All right, and limits say that you can split up the function like so if it's adding or subtracting. So let's look at these each one at a time. This first one's going to give us a 1. As I told you, that's a rule. We learned the squeeze theorem way back when and showed that sine x over x when you approach 0 equals 1. This one right here, best way I can think of to do this is think about the 1 over x graph. The 1 over x graph has an asymptote right at x equals 0. It also has a horizontal asymptote. And your graph goes something like this. Oops. And so if we're approaching 0 from the right, this function is approaching infinity. So it looks like we have infinity. And infinity plus 1 is still infinity. So that's going to be our answer. Now you might be wondering, why is this problem in here? It's probably in here to try to trick you to use the L'Hopital's rule. And you can't, because we don't have an indeterminate form. So don't fall into that trap. All right, next one. All right, hopefully this is the last limit. I'm not excited about limits, but anyways, it's not that bad, I suppose. All right, let's first directly substitute in 0. If I plug 0 into this, that would be e to the 0 power, which is 1. And then I subtract 1. And then if I multiply 3 times 0, I get 0, so it would be minus 0. And on the bottom, I would get 0 if I plug in 0 to the x squared. Since 1 minus 1 equals 0, we get an indeterminate form, 0 divided by 0, which we're really excited about, so now we can use L'Hopital's rule. So let's take the derivative of the top, and then the derivative of the bottom. All right, so the derivative of the top, the derivative of e to the x is just e to the x, so we just write e to the 3x. But since we have more than just x in the numerator, we have to multiply this by the derivative of 3x, which is just 3. The derivative of 1 is gone, and the derivative of 3x is negative 3. All right, so the derivative of 1 is gone. Well, you guys get that. All right, now the bottom. I get 2x. Now let's take the limit of this as x approaches 0 from the positive side. Right now, I'm not worried about the positive side, but let's just plug in 0 to see what happens. If I plug 0 into this one, that would be 3 times 1, because anything raised to 0 power is 1. Then I'm subtracting 3. And the bottom, I get 0 as well. So it looks like I get 0 over 0. Ooh. Do we have to use L'Hopital's rule again? Yes, we do. So we take the derivative of the top and bottom yet again, and we're crossing our fingers, hoping it works this time. It didn't work 2 problems ago, but let's see what happens. The derivative of the first one is going to be e to the 3x again. But this time we have to multiply the 3 times the 3, so that's actually going to be a 9. The minus 3 goes away, and then I'm left with a 2 on the bottom. So I have a 9 times e to the raised to the 3x. If I plug in 0 this time, let's see what happens. Ooh, something different. Ooh. All right, we get 9 times 1 on the top, because anything, that becomes 0. Anything raised to 0 is 1. Negative 2, so it's 9 divided by 2, which is the same as 4.5. That's our answer.